Alright, now for a security example, we're going to go over something called row hammer or DRAM disturbance errors. Basically, this is a technique in order to change the bits of other programs that are running inside your program. So this is in a way, a privilege escalation issue because it's able to modify other ones, and it can be used to do remote execution, although it's pretty hard to do that. So this is presented by myself, Dr. Paul West, and totally taken without permission from these people right here who worked for those two companies and Carnegie Mellon. I don't know if that was a university or the place. Alright, so the idea is that you first, in order to understand how this vulnerability occurs, you must understand a little bit about DRAMs, which we haven't gone into. But DRAMs are working by a row of cells. They're really just capacitors that sit amongst one or another. And the way this works is you may have they call them a victim row. You might have the row that you're computing on, and the idea is that this piece of memory reading and writing to it will try and flip the bits of this piece of memory on this side. Now, the reason that this is a problem is that this may be your processor's memory, and this might be, I don't know, the security key that people are trying to use. So you might be able to actually flip the bits for a security key if you know how to do this. Let's see, we exposed the evidence and prevalence of the errors. So they found out that 129 modules that they were using were affected. Affects most modules 2010 vintage or later. So they talk about how they can go about it and ways to prevent it. So some historical context. DRAM came out in 68, great, 71, Intel commercialized it. The idea is you have a cell and a bit line, and then this bit line will set the actual cell. This big fat metal line with full level signals running over a storage node is where this is going to be problematic. Early DRAMs with row-to-row coupling, and this was an observation or something that they came up with. We observed row-to-row coupling, and then Intel patent mentioned row hammer as a problem in 2014. So this has been around for a while. This is another slide. So let's do a demonstration. So the idea is you have x86, you have your DRAM module, which is storing your memory. This is DDR3. You have to avoid cache hits, and this is something you can actually do inside of x86 because they have an instruction called flush. So you can constantly just be flushing the cache. And you need to avoid row hits, so you need to make sure you to X, so you read from Y in order to affect the bits on there. So the idea, and here's some, x86 instructions. You want to move to, whoops, didn't mean to do that. X value to EAX, so you want to move here, and then you want to move to Y down here, and then you want to keep flushing these two so that they don't get stored on the CPU. They're constantly being written to DRAM. And then mfence is just a way to make sure that you pause until cflush is done, and then you jump back up to loop. So just to make this a little more sense, you write to certain memory addresses, you flush it out of the cache, which forces it to write to memory. You call mfence, which means that you wait for it to come back from memory before you do all this again. The reason for this is a lot of times when you call cflush, it begins the operation of flush it to memory, but it's going to continue execution because it can, and it's trying to be more high performance. So this is just a way to make sure that it is flushing it. Man, these slides got messed up. Can I move this in any way, shape, or form? Nope. All right. So errors, they tested on different processors, and AMD is also vulnerable to this. It's not actually the processor that's vulnerable if you think about it. It's actually the DRAM, but they wanted to say that different processors can have different performance metrics on how quickly to do this. So the OS page is 4 kilobytes. You'll talk about that inside of operating system, which fits inside a common DRAM row, which is 8 kilobytes. And this specification of a DRAM row is actually specified inside of the JDEC specification. So this is a disturbance attack, and it tries to disturb different values, and they made a proof of concept here. So the cause one is this electromagnetic coupling. The idea, if you recall from those fat wires earlier, excuse me, is that they're so close together or coupled that they can do what's called a conductive bridge, which will conduct what one value is being set to in order to influence what the other one. And this can cause a hot carrier injection, aka while it's running, it can cause a problem. So characterization, So they did a little quick test. So they had PC with a little FPGA board. All right, what's an FPGA? An FPGA is a way to dynamically test different processor designs. It's very common for doing a type of simulation or prototyping. The idea is we can take our Verilog and it writes it to an actual FPGA board, so you can actually see or test your processor in something that would be close to real life. Now I say close to real life because FPGA boards are usually 4 times slower than actually burning it to silicon. So usually FPGAs make a poor final solution, but they're still used a lot because of their programming capability. And so they wanted to program a little test engine in order to see if they could flip the bits in DRAM with an FPGA board. So they had a bunch of FPGAs. Here's the PC that would program them. A little heater, I guess in case to warm it up because it got cold. And they're just, now inside of security is very common for people to protect what companies are vulnerable to what, because they want to allow companies, or I should say it's common courtesy, to give companies time in order to solve these problems before they fully release the issue. But the security people want to alert everyone, so they go ahead and give these alerts out. That is just a common courtesy when you're programming it, so please don't actually give the names of companies out if you find any of these. So company A, B, C, they found these different vulnerabilities, total of 129, and these were from 2008 to 2014 and different capacities. Most modules are at risk, they found out. There's errors versus the vintage. There are a couple that don't have it. Let's see if they talk about it a little bit more. They talk about the number of errors. So 86% here, 83 and 88. In other words, if you buy from one of these 3 companies, chances are your memory is vulnerable to this attack. First appeared in 2010, and let's see, all modules from 2012 to 2013 are vulnerable. 2 types of errors. You are basically, this should be an arrow, 1 to 0 and 0 to 1. A given cell suffers only one type, so 2 different types of charge. There's the true and the anti-charge. So this works with what's called a capacitor, which means if the capacitor has a charge, it's a 1. If it doesn't have a charge, it's a 0. And although it can be the other way around, depending on the manufacturer's design choice. True cells, aka the ones that are charged with 1, can only go from 1 to 0, and anti-cells can only go from 0 to 1. This should be blatantly obvious, but they wanted to make sure that everyone was on the same page. So the idea, the way this is work, is that any adjacent row can actually affect one or another, but if the distance is, it looks like 2 or 7, it doesn't actually affect. It has to be 1 to the left or 1 to the right in order for them to actually be affected, and that's what they mean by adjacent. Alright, they go into a lot of details about how quickly the refresh rate works and whatnot. We're going to go and skip that for brevity, and we don't need to go into too much details because we're not actually technical engineers. They wanted, what was the point of this one? Oh, they were talking about how quickly you had to access memory in order to increase the chance of an error. They were just pointing out here, once your processor slows down to a certain amount, you can no longer take advantage of rowhammer. So a simple way to fix this is to slow down your processor. Hopefully people realize that that is not necessarily a viable or desired alternative. Alright, they talked about this with refresh. The point here is that if your refresh was very, very high or very quickly, or I'm sorry, very high. Now what refresh is since the DRAM module is using capacitor in order to store the variable, the capacitor does leak voltage over time. So in order to retain the voltage, DRAM has to pause whatever access to memory and refresh or recharge all the capacitors that are at 1. And the refresh rate is how often we need to refresh it. So if your refresh rate is very high, aka you don't have to do it very often, you usually have a ton of errors. While if it's very your refresh rate is very high, or in other words, the value is very low for how often you do it, the number of errors does diminish. And you got to do some data patterns, of course. We're going to skip that for a moment, or skip that for now because we don't need to. So naive solutions for this is throttle access time. That was, I say, toggle your DRAM so that at least 500 nanoseconds or slow down your processor. Again, these are not desirable. You can refresh more quickly, but the problem with the refresh is every time the memory refreshes, it's not allowed to access anything, so this slows down memory again. So again, these two solutions are naive and have a significant overhead to performance and power, because you actually have to improve or increase your power, especially for the second one, in order to cause a refresh. So neither of these solutions are desirable. Unfortunately, yeah, most modules risk, we talked about that, and let's see. We're going to skip that for now, or skip that period, and this one as well. So other solutions, you can make better DRAM chips, that'll make it more costly, refresh frequently, which is power, sophisticated EEC. So what EEC is error correction codes in order to make sure that the modules didn't change, and you probably could execute this every time you do a refresh. Fortunately, that increases cost and power. You can also have access counters, which will take basically the idea that if you access one of these a certain number of times within a certain nanoseconds, the idea is you would stop it or slow down that one type of access, because the access should never be faster than 500 nanoseconds, because the CPU's cache should be caching it. So you kind of know that there's something weird going on if the access time does become that high, which is why access counters do work, but again, increases cost because you have to have the counters, you have to power the counters, and now it becomes way more complex because you have to add circuitry in order to take advantage of these counters. So para, probably just another solution. Their solution is after closing a row activated, refresh one of its neighboring with a low probability. The reason why this does work is that the idea is that it's going to refresh it with a certain probability, which will stop a row hammer from actually working correctly, because in order for a row hammer to work, it has to really hit that row over and over again very, very quickly. So by having a probability, aka you're going to refresh that row just automatically after a certain number of times, it will decrease or substantially remove or mitigate the chances of row hammer actually doing a mitigation or affecting it. And if you tweak these numbers correctly, as they found out, you can actually eliminate row hammer. Now, this does have a bit of a performance and power cost to it, but it's nowhere near what the previous ones were. All right. And they talk about why para is a little better, but I highlighted that already. All right, so these disturbances are widespread, and due to difficulties with DRAM scaling, new and other types of failures have occurred because they're trying to pack these capacitors closer and closer together, and as you do that, this idea of row hammer disturbances does increase. And that's the end. Any more slides? All right, so the question is, why is this architecture? Well, we're talking about memory and at the architecture level, so obviously this is. How concerned should we be nowadays? Not that concerned. In order for the row hammer to work, notice that you had to have a program that works a certain way, so you are going to have to be running a rogue program on your processor, and usually there's security controls that will remove that from happening, but people still do run rogue programs on their machines, which probably could exploit something else as well. Also, DRAM manufacturers are aware of this, and they have been working on modules to correct it, and overall the rate of this error is decreasing, although it still does exist. All right, that's it for row hammer. Hey, look, 13.